In this deck, we focus on the Vessel Re-stow Problem during transshipment operations. The core task is to reorganize how containers are positioned on a vessel at an intermediate port so that later discharge operations are efficient and the vessel remains safe. We will move from a mixed integer programming formulation to practical heuristics, ant colony optimization, deep reinforcement learning, a digital twin, a human and artificial intelligence partnership, and a quantum optimization framing. The goal is to reorganize container configurations at an intermediate transshipment port. The outcome you want is a clean discharge sequence for the remaining ports, with stable weight distribution and minimal operational disruption. At the same time, you must minimize container moves and handling cost because every extra move consumes crane capacity and increases delay and damage risk. Restow is required when the current stowage was optimized for a previous loading sequence, but the vessel now faces a different discharge order and additional loading requirements at the hub. In a transshipment environment, every unnecessary move can create cascading delays. That is why restow is both an optimization problem and an operational risk management problem. The scenario is set at the port of Singapore. The vessel is ever given to with an 18,000 TEU capacity, carrying containers bound for multiple Asian ports. Those discharge ports include Hong Kong, Shanghai, Busan, and Tokyo. The operation is constrained by a limited port stay window of 18 hours for restow and new loading. The operation must satisfy vessel stability through weight distribution, and it must respect crane accessibility patterns, because not all moves are equally easy within a tight port call. It must also respect the discharge port sequence so earlier ports remain accessible, comply with hazardous compatibility rules, and minimize shifts within the 18-hour operational window. Two cost drivers dominate. The first is handling cost for each container moved to a target position. The second is the penalty for moving the same container multiple times. The overall objective is fewer moves, safer weight distribution, and better discharge accessibility for the remaining voyage. This deck is organized by tiers. Tier 1 is a mixed integer programming formulation. Tier 2 is a constructive priority heuristic. Tier 3 uses ant colony optimization. Tier 4 uses deep reinforcement learning. Tier 5 is an integrated digital twin. Tier 7 is a human and artificial intelligence symbiotic partnership. Tier 9 introduces a quantum optimization framing. Tier 1 models restow as an assignment and movement planning problem. You decide where each container ends up, and you can also represent when moves occur within the port stay. The objective is to minimize total move cost plus penalties for multiple moves. This is a strong baseline because it makes assumptions explicit and enforces constraints cleanly. Restow is not just rearranging containers for neatness. The model must capture discharge accessibility and vessel safety at the same time. Operationally, a usable formulation must represent the slot system, the port sequence, the move sequence, inside the port window, and feasibility filters that prevent unsafe or impossible outcomes. This slide defines the main objects in the model: containers, stow positions, discharge ports, and time periods. These sets give the model a vocabulary to express where containers can go, what discharge order must be respected, and how moves are scheduled. Containers are the items you may relocate. Stow positions are the physical bay row tier slots on the vessel. Ports define the discharge order that drives accessibility, and time periods represent the move sequence inside the 18-hour port window. This slide introduces the variables that represent assignment and movement decisions. In practical terms, these variables determine the final plan and the operational effort needed to execute it. The assignment variable answers where each container ends up. The move over time variable answers when the move is executed. The move count variable captures how many times a container is touched, which is a direct driver of cost and risk in real operations. This slide shows the objective that combines handling costs and penalties for multiple moves. The message is that a good plan is not only feasible, it is also cost-efficient and avoids repeated reshuffles of the same containers. Move cost captures crane work and operational time. Multiple move penalty discourages plans that repeatedly reshuffle the same container. This trade-off pushes the optimizer toward a plan that is efficient now and remains workable for later discharge at downstream ports. This slide enforces that each container is assigned exactly once. Operationally, it prevents missing containers and prevents duplicating a container in multiple positions. Without an assignment constraint, an optimization model can create unrealistic outputs, such as leaving a container unplaced or placing it twice. This constraint enforces physical completeness. Every container ends in exactly one place. This slide enforces that a position can hold at most one container in the simplified model. Operationally, it prevents collisions where two containers are assigned to the same physical slot. If you allow more than one container per slot, the solution may look cheap, but becomes physically impossible. This constraint blocks that failure mode and keeps the plan implementable on the vessel. This slide introduces weight limits that restrict unsafe loading patterns. In practice, weight limits protect vessel stability and structural safety, and they prevent concentrating heavy loads in risky regions. Weight limits protect stability and structural margins. If you violate them, a plan may be operationally fast but unsafe to sail. So even if an assignment improves accessibility, it must remain within safety limits. This slide expresses accessibility constraints that restrict which slots are allowed for containers of a given discharge port. Operationally, it encodes the core rule. Early discharge cargo must remain accessible without excessive rehandling. Accessibility constraints prevent burying early discharge cargo under later discharge cargo. This is the formal mechanism that avoids future reshuffles and avoids wasting crane time at downstream ports. This figure visualizes the Re-stow structure and flow between bays and positions. Use it to connect the abstract constraints to the physical layout that cranes and planners deal with during a port call. The example uses 5 bays and 12 containers. The current configuration has containers for Hong Kong, mixed with containers for Shanghai. The target configuration clusters by discharge port, so that Hong Kong containers are grouped and Shanghai containers are grouped, reducing future reshuffles. The example reports that the optimal solution requires 3 container moves with total cost $450. That cost is computed as 3 moves times $150 per move, illustrating how quickly costs scale with unnecessary reshuffles. Tier 2 uses a constructive heuristic that assigns a priority score to each container based on discharge urgency, accessibility, and movement complexity. This approach is designed for speed. It produces a practical plan quickly when you cannot afford long solve times. This slide shows a priority score concept that combines urgency, accessibility, and move cost. Operationally, it turns several planning concerns into a single ranking, so the heuristic can decide what to move first. This figure summarizes the loop of scoring, selecting, assigning, and updating the configuration. The key message is that the heuristic is an iterative construction process rather than a single static rule. This code slide shows how the method computes priority and then greedily assigns containers to the best available positions. The important operational detail is that the assignment is guided by a position quality evaluation that reflects discharge order and feasibility. For 100 containers requiring re-stow, the example reports priority processing time of 0.15 seconds and position assignment time of 2.3 seconds. It reports a movement plan with 23 moves compared to 45 moves with random assignment, corresponding to a 48% handling cost reduction. Tier 3 uses anti-colony optimization. Candidate assignments are built probabilistically using pheromone and heuristic desirability. Over iterations, the method reinforces good placement patterns, such as discharge port clustering, while still respecting constraints. This slide shows the probability mechanism that balances pheromone strength and heuristic desirability. Evaporation prevents early lock-in, and pheromone deposit reinforces assignments that reduce cost. This figure visualizes the ant colony optimization workflow for re-stow. It highlights repeated construction, evaluation, and pheromone update as the engine that improves solution quality. This code slide introduces the optimizer class and the main parameters for ants, the iterations, pheromone influence, and evaporation. It also shows the pheromone matrix and heuristic matrix as the state the algorithm learns over time. This part shows how the algorithm builds a solution by selecting positions probabilistically from the remaining available set. Operationally, this makes the search explore alternatives rather than always taking the same greedy choice. This part shows how pheromones are updated based on solution fitness. Better solutions deposit more pheromone, so future ants are more likely to repeat the underlying assignment patterns. This part shows the main optimization loop over iterations and how the best solution is tracked. The loop structure is what allows the method to improve over time rather than stopping at the first feasible plan. This part shows the evaluation idea. Total cost includes movement cost, plus stability and sequence penalties. Operationally, the evaluation function is where you encode what you care about most, including stability and discharge order. The example reports a test with 200 containers across 15 bays, using 30 ants over 150 iterations. It reports 67 moves with total cost $8,450, convergence after 89 iterations, and a 34% improvement over an initial greedy solution. Tier 4 uses deep reinforcement learning to treat re-stow as sequential decisions. The agent learns which container to move and where to move it. The goal is to learn strategies that may look non-obvious locally but reduce total cost and delay over the full operation. This slide defines the state as a structured representation including occupancy, port encoding, remaining discharge sequence weight map, and remaining time. Operationally, the state must capture both spatial layout and time pressure, so the policy can act under port window constraints. This slide defines an action as selecting a container identifier, plus a source position and a target position. In real operations, this corresponds directly to a crane move decision, which is why action feasibility is crucial. This slide defines a reward that penalizes movement cost and stability penalty, and rewards discharge efficiency improvements. Operationally, reward design aligns learning with real goals like fewer reshuffles and safer weight distribution. This figure shows the reinforcement learning loop of state, action, reward, and policy update. A key implementation requirement is invalid action masking, so the agent cannot select physically impossible moves. This code slide outlines a deep queue network using convolutional layers for a spatial vessel grid with 4 channels. It then combines spatial features with additional features to output action values. This part shows the agent setup with experience replay, epsilon greedy exploration, discounting, and a target network. Operationally, the target network stabilizes learning, so the policy does not oscillate unpredictably. This part shows action selection and explicit masking of invalid actions. This is essential for re-stow because many action combinations are infeasible due to occupancy and constraints. This part shows the replay training step: sampling a batch, computing targets, minimizing error, and applying gradient clipping. These mechanics help the agent learn reliably from simulated re-stow experience. This part shows the training loop over episodes with periodic training steps and exploration decay. In operational terms, each episode is a simulated port call where the agent learns movement patterns that reduce total cost.